Let's get started anyway. See more here. I was gonna start with the example I ended with the last time. I said that you can look for homework, and I don't know if I was serious or just joking, because I was sure that if I say you can do it for homework, it's almost like saying don't do it, or maybe if I said don't do it, then somebody might do it. But let's look at it for real now, because it's sort of illustrating example of very simple case of SVD. So what the example I actually did last time was SVD of a matrix, of a 2x2 matrix that was full rank, right? And I want to do an example of one that's not full rank, so you see where the null spaces show up. I say null spaces because the left null space and the right null space, or the right is default, so you don't even say it. So let's do like 1-on-1 or 1-on-2 or 1-on-3 session. So what rank is this matrix? Let's just talk about it for a little bit before I do the SVD. So what is the rank of this matrix?
1.
That's right. I was hoping you'll do that. All right, what is the row space? Should have it faster than I write it down. So what is the row space? Row space is a subspace, right? How do I represent it? By picking a non-zero vector in it, the basis vector in it, right? So the row space is what? Well, it has to be a vector, right? So 1, 1, yes. Slightly tricky question. or I guess I could write it like this, like a column vector, right? So how about the column space? It's getting like a little bit more tricky every question. 1, 0? 2, 1, yeah. I take 2, 1. Or it could be 4, 2, right? Or it could be -2, -1, or 1 and 1/2, or any non-zero multiple, right? Would do. How about the null space? So that means the right null space, right? So all the vectors which I multiply from the right, all the x's such that ax equals 0. So what I'll get there? I guess I should have also said that obviously the dimension of the row space and the dimension of the column space is 1, right? The dimension of the null space therefore also has to be 1, right? We have this 4 fundamental subspaces thing that it's 2 minus the dimension of that, so it's dimension 1. What is the basis for the null space? It's like fairly, so we were looking, huh?
1, -2.
So that would be the left one. I'm asking for the right one, which is all the x's such that ax is 0. So like give me one x like that, yeah? 1, -1, yes. And that's also the basis for the null space. Because if I multiply it by whatever, then this is still true, right? And the left null space, I think that's what you were saying before. So left null space means all y such that yta is 0. That's right, yes. 1, -2, or could as well be -1 and 2, right? So this is how the 4 fundamental subspaces of this matrix look like, and let's see how do we see them in SVD, right? They should show up in SVD, as I was trying to explain the last time. So let's just do it. For a 2x2 matrix, it's very simple, and we can just do it on a paper. So you remember, what do? We take the ATA matrix, which in this case is just 5, 5, 5, 5. So you can easily verify. And we compute its eigenvalues. Eigenvalues are this. So the second eigen, notice it has to be 0, right? Because this matrix is not full rank. So that's, if there is an eigenvalue 0, that means that the matrix is singular. And you could certainly give me a reason, right? Could you? I said that if there is an eigenvalue 0, then the matrix is certainly singular. Why is that? Well, eigenvalues and eigenvectors, they satisfy this, right? Where x is the eigenvector and lambda is the eigenvalue. If the eigenvalue happens to be 0, well then this is just 0, right? So that means there is and the eigenvector must be a non-zero vector, right? So that means that the matrix must be singular. It cannot have full rank, so it's not invertible. Anyway, that was just side comment. So the eigenvector corresponding to the first eigenvalue is, I already computed it for you. We can probably just verify it. And v2 would be -1, 1. So let's just check it. So ATA v1 is what? It's 10, 10, right? So yeah, that exactly corresponds to this eigenvalue. And -1, 1, that's exactly 0. So indeed, it corresponds to the 0 eigenvalue. So that's good. What we want to do is normalize v1 and v2. So the unit version of v1, what do you think is going to be the unit version of v1? That's a stupid question. I will just write it. 1 over square root of 2, 1, 1. And if I make a unit length version of v2, that means divided by its length. That's the same thing. 1 over -1, 1. So these guys are the right singular vectors. And those are the singular values squared. Right? Is that right? Yes. So the singular values are what? Those are eigenvalues of ATA. So what are the singular values of the matrix A? Which that's the matrix I'm really interested in.
0.
Yeah. Yeah, so the singular values are 0 and square root of that. Yeah. Okay, so those were the right singular vectors. Now let's take a look at the left singular vectors. So there we need to do AAT, which if we do the math, we see it's 8, 4, 4, 2. And guess what? Guess what are going to be the eigenvalues there? Have you been paying attention last time? What is lambda 1 and lambda 2? It's very simple. It's actually the same thing. Because one thing I said the last time is that they have to be the same. The eigenvalues of ATA and AAT are, interestingly enough, the same. And there was a reason to it. Okay, so what is U1? You know what, let me give this tilde so that I can call U1 the normalized one. So the U1 will be 2, 1. We could compute this. I'm just skipping the computation of the eigenvalues in the interest of time. But you should know how to compute it, right? All that. For 2 by 2 matrices, it's very simple. So let's check it. If I do AAT times U1 tilde, what do I get? I get 8, so I get 16 plus 4 is 20, which is good because it's 10 times 2, right? And here I get 8 plus 2 is 10, which is also good because it's 10 times 1. So that is correct. So I'm just verifying that U1 tilde is indeed the eigenvector of AAT with eigenvalue 10. Just to make sure I didn't make some mistake. And I guess I should check also U2, but let's just trust it. So if I want to take the normalized versions, U1 hat, so that's going to be 1 over square root of 5, 2 and 1, right? That's just making it unit length. Square root of 5, 1 and minus 2. Yes, so those are the left singular vectors. So from this, I have enough information to write the SVD of the original matrix A, 2, 2, 1, 1. So this was my original A. I can even write it here like this. And so what comes first in SVD? the U matrix, right? So how is the U matrix going to look like? What shall I put there? U1 and U2, right? So it's gonna be 2, 1, and 1 minus 2. This is my normalized U1 vector. That's why I have this 1 over square root of 5. And this is my normalized U2 vector. Yeah, I need to go faster. I still have tons of applications to go through. I like to explain it nicely and slowly. But so here is going to be the first singular value, which as we established is square root of 10. And this is a square root of 0, which is just 0. So this is the U matrix. This is the sigma matrix. And here what we have is the V matrix. Here we need to be just a little bit careful, because there is the transposition thing. Remember that? So what I do here is I need to write the V1 into the first row. So this is 1, 1 here. Here is my V1. So this is my V1 normalized. I guess I should make it like normalized like this. And there is the V2, which is minus 1, 1. V2. Okay. Oh, no, I don't remember if I put the recording on. Let me check. Yeah, I did. Okay, good. So this is my V transposed matrix. In the V matrix, you would just put the V's in the columns, but here we have the V transpose matrix, and you could verify that if you do this matrix multiplication, you will get back exactly A. And now watch this. So here previously we discussed what are the properties of the matrix, right? And from SVD you can immediately see all of this. So we discussed what is the rank. The rank you can see here. There is 1, 0, 1 non-zero. So the 1 non-zero means it's rank 1. The row space, where is the row space? The row space is here. Right? So we said before that the U and V matrices, then they split in two. Here is the row space basis, and here is the column space basis. Indeed, this first vector here is the column space basis. Right? That's because it's rank 1. It splits in rank 1 matrix. It's sort of stupid. It's so simple, but that's what it is. The null space we have right here. That's the basis of the null space. This is what we discussed previously in general for any matrix. So here is a specific example that you see that really is true. And here, right here, this is the basis for the left null space. So all these vectors, they just appear in SVD. So for more complicated matrix, you couldn't do it like we did it here, just like thinking about it. Oh yeah, obviously the column space is like this, the null space is like that, right? But if you just run SVD in MATLAB, the full SVD, it just immediately exposes the bases for all the 4 fundamental subspaces. That's the real point of SVD as long as linear algebra is concerned. And what I would like to do today is to go through some examples of using SVD. A question?
Does the ordering of the vectors in the matrix matter?
Ah, that's an excellent question. So here it doesn't, because it's just one-dimensional the hard matrix and one-dimensional the complement thing, right? But in a bigger matrix, it would matter. And how would it matter? It would be by ordering of the singular values, right? So if I have some large matrix, which results in some large sigma with some sigma 1, sigma 2, sigma 3, and so on, up to sigma r, then what I could be doing, I could be changing order of the columns in U, or changing order in the rows of VT, and swapping the singular values accordingly. Actually, it will be very clear from the matrix multiplication formula, which I will show in a second. But you can see it even from directly from matrix multiplication. So the order is only given by convention. So in theory, if I did not require a specific ordering convention from the single values, then I could produce lots of single value decompositions, right? I could just permute these things. Even here, what I could do, I could do this, right? I could just say that sigma is this, then I would flip the columns and flip the rows, and I would have like another single value decomposition. So that's why there exists the convention, which I was always saying before, that we order the single values like this. Basically in non-decreasing order. They can also be the same. That signifies some funny things if the single values are the same. And usually you have a bunch of zeros at the end. Unless it's full ranked. Okay?
So when we... Okay, never mind. You already answered the question.
Okay. All right, so let's take a look at some applications, unless someone else has some, because this was a good question. Oh yeah, there is another. Okay, I don't want to get into the details. There is one other subtlety that sometimes you might allow a negative single values, which is sometimes useful in some applications, but let's not go into all the details. Let's do the applications first. If you still have time, you can do some more finickiness of SVDs. So the standard case is like that you just order the single values, and that takes care of most of the issues. There are still some issues if some of the single values are the same. If I have like repeated single values, which makes the SVD slightly non-unique, but okay, let's do the examples. That's more fun, I guarantee you. So let's talk about the optimal K-rank approximation of a matrix. I have some slides on it, but I first want to give you an idea what is going on here. So let's consider this example. Let's say I have an image, 256 by 256 monochrome image, which I can of course represent by a matrix, right? So I can take a matrix which is from R 256, so I have some decent resolution, 256, and or it could be like just from 0 and 1, right? Like the intensity. And that will give me some decent image, right? With something. Now let's say I want to compress this image using SVD. SVD is like I guess the corniest application. So what did I say? Data compression is the corniest application of SVD, but very cool actually. So let's say I want to compress this image, and I want to compress it by finding a rank K approximation of the matrix. So the simplest case would be rank 1 approximation. Rank 1 approximation would mean to just find vectors A and B such that A, B, T, the outer product, that's a matrix, right? If A and B are 256 vectors, then this would be a 256 by 256 matrix. And I would like to find these A and B's which give me the matrix which is the best approximation of A. So what do I mean by best approximation? I need to clarify this. So I can measure the quality of approximation, for example, using the Frobenius norm. Do you remember the Frobenius norm? The Frobenius norm of f squared is the sum over all elements of A squared. So if I want to measure the quality of approximation, if I want to see how good of an approximation A, B, T of A is, then all I need to do is look at the Frobenius norm of the difference. Because if this is close to 0 matrix, then it's probably a good approximation, right? I mean, it's also easy to just write it out, right? If I have A minus B, then Frobenius norm squared is obviously Aij minus Bij squared, right? So it just wants the two matrices to be the same on every element, which is probably a good or intuitively reasonable quality metric. Okay, so now the problem is, given A, which can be really any matrix, doesn't have to be image, or doesn't even have to be square. I want to find, get the notation right, find matrix AK such that, or maybe I can say, oh my goodness, which minimizes AK minus A for B is norm squared, subject to, or such that the rank of AK is K. That's why I give it the subscript K. Or I could say, which solves the following minimization problem. Minimize AK minus A for B is norm squared such that the rank of AK is fixed to K. Have you seen this before, this problem? Low rank matrix approximation. It's very cool, and it's actually even a more complicated version of this is like a sort of hot topic in like statistics and so on. When you consider sparse low rank matrix approximation, it's sort of pretty cool stuff. So this is the basic thing. So this problem is completely solved. It was solved in 1936. It was probably solved before that, but the standard solution from 1936 is the Eckart-Young theorem. And maybe I'll just tell you the solution first and then show the slides. The solution is that you take the SVD of the matrix A and then you zero all but the first K singular values. So you take the SVD. So the sigma has some single values, sigma 1, sigma 2, sigma 3 to sigma r. And the optimal approximation AK has the same U and V, or this would be V transpose, right? And here you just kill 0 as many singular values as you need and until you get the desired rank. So if you want rank 1, you would just zero out everything but the first one. Yeah?
And this works because they're ordered in like decreasing order? Correct. That,
this convention is almost universally assumed. That's right. Otherwise I would have to be more careful and say that I zero out the smallest singular values. Yeah, great question. Thanks. So another way we can look at it is by looking at a different way of doing matrix multiplication, a different way to write out the matrix multiplication formula. That's called the outer product, or maybe just as a sum of outer products. So matrix multiplication, you can understand it as dot products or a sum of outer products. I mean, it's really quite simple, because if you look at it, if I have two matrices and they are m by n and n by k, so I can really multiply them. So what is the I and j component of the result? Well, that's just by definition of matrix multiplication. It's AIL times BLJ, right? So it means I take ith row and go in columns, and I take lth columns of B and go in rows, right? And I sum all of that. So that's essentially, that's a dot product of ith row of A and jth column of B, okay? Now what I have here is the sum of outer products of AI, BI transpose. So maybe I should describe what I mean by that. So the A's are the columns of matrix A. This is what I'm drawing here. And the B's are the rows B1 transpose, and so on up to B also N transpose, right? Because this one is M by N and this one is N by K. So the A's are the columns, B's are the rows, and this is doing the individual outer products. And if I look what I have, actually, let me give this L, so I don't have a confusion of indices here. So this is L going from 1 to N, right? And every single one of them is just an outer product of the two vectors. So the first one is I take A1 and do B1t, then A2 plus B2t, and so on. So if I take a look what is on the I and jth element, what is on the ith row and jth column of this matrix, it turns out that that's nothing really than looking at element number I of the L vector and element number j of the B vector. So that's really the same thing. In other words, I need to really go a little bit faster. This is just like a different way of like rearranging the additions and multiplications in matrix multiplication. So when you apply this sum of outer products to SVD, get sort of nice expression, because we have the matrices U, V, right? The left singular values, right singular values, and the singular, left singular vectors, right singular vectors, and singular values, and we sum all of them together. The singular values essentially just scale each of these contributions. That's because that's a diagonal matrix, right? So if we have the SVD of A in the form of U dVt or U sigma Vt, then I can, using that formula from the previous slide, I can write it like this. And here I can nicely say what is the best rank K approximation of that matrix. So again, here I assume that the sigma 1 is the biggest one, sigma 2 is the smaller one, and so on, like this. If not stated otherwise, you should always assume that's the case, that the singular values are ordered like that. That's like MATLAB gives you that ordering and so on. And the best rank K approximation basically means to truncate or zero all the singular values beyond K, where K is my allowed rank. To prove this is not completely trivial. That's what essentially the Eckhart-Young theorem is about. I could do a proof, but I think it would take a little bit, so I'm not gonna do it. Not now. So this is sort of cool if you use it for data compression, SVD. It's sort of like, that's what it's sort of begging for, right? In terms of the image matrix, if I have this case of image matrix, essentially it means that if I only did rank 1 approximation, that means that I have one image. There was something on that image, right? And I just represented it like using what? Using just 2 column vectors. If I only did rank 1 approximation, that's all I need, right? So if the rank 1 approximation is really good, then I have achieved like a very, very big compression, right? Because here I have 65, 536 like bytes or float numbers, and here I have just 512, right? So I compressed quite a lot. Now this approximation wouldn't be particularly good, so I'll probably want a higher rank approximation, which means that I'm approximating the image with a product of 2 matrices which look like this. And from the theory, you also know what is in these matrices, right? These are some linear combinations of the columns of the image, and those are some linear combinations of the rows from the image. And what sort of linear combinations do you think there will be? That sort of, these are the best matrices, such that after I multiply them, I get as close as possible to my image, right? This is minimized Frobenius norm squared, right? And this is what I'm minimizing over. So essentially, this sort of extracts some sort of features from the image. You could think about it that way, right? Like if I have like a thick house or something like that, which has like lots of structure like this, then probably this will somehow show up here, right? Because what this matrix multiplication is doing, it's just taking linear combinations. You can look at it, every column here is just doing linear combinations of the rows here, right? So in the rows, there will be some sort of fundamental parts or features of that image. Does that make intuitively sense? That's what all these, that's the story, that's the main narrative all the examples are about. So let me do some more examples and maybe it will sink in better. So one simple example is finding patterns in data. PCA stands for Principal Component Analysis. Don't worry so much about the terminology. The point is that the SVD is such a important thing that has been used in multiple areas and multiple fields. Like in statistics, it's usually called PCA. In like image processing, some people call it Carhoon and Loewe transformation. And there are some slight nuances, but the idea is still the same. So don't get confused by this terminology that like this is something different. No, it's all the time, it's the same basic idea with some slight variations here and there. So let's take a look at the example. So you are studying bears, and you have some measurements on bears when you measured height and weight of a bear. So this is like sort of statisticsy sort of thing. And of course you suspect there is a relationship between the two, a strong correlation. And one way we can discover this correlation is, well, by plotting it, right? So we can do a plot like this, and we see something, get a graph like that, right? So here you can see strong linear correlation, right? The taller the bear is, the heavier it will be, or the other way around. I don't really know. Doesn't matter. And if we want to do it in a more principled way than just staring at a graph, then we can just write down the matrix of the data. That's the main point. We are forming a matrix from our data. So the matrix has some semantics to it, and therefore also the SVD will have some. The SVD will tell us something about our problem. In this case, if we form this data matrix like this, so we put all the measurements in the columns. So here I put the X would be the weight and the Y would be the height of the bear. And so this would be my measurements in the columns. And here is the number of my data, the number of bears I measured. Okay. And if I do the SVD of the matrix, then for a case like this, where there is a strong linear correlation, I'll get single values sigma 1 and sigma 2, where the sigma 2 should be pretty damn small, right? Because if there is a strong linear relationship, then y's should be very accurately linearly predicted from x's, which means that this matrix maybe will not be exactly rank 1, but will be close to rank 1. And this means that the sigma 2 will be close to 0. So in general, SVD or PCA or whatever you want to call it helps us discover linear patterns in data, which is very cool. That's also what happened in the matrix or image compression example, essentially. It sort of discovered the linear patterns there and used it to compress the data. It's sort of cool. So in 2D, it's easy, right? You could just say, well, we can just plot it and then fit it a line or whatever. But SVD is powerful because it can let you go to any number of dimensions, right? I have one more example when we just go to a little bit higher dimension. Say you work on Wall Street and you are investigating prices of gas, delicious high fructose corn syrup, and Snickers bars. And you suspect there is a correlation between the three. There most likely is, right? So what you do the same thing as you did with bears, except that now our measurements have 3 values, right? The price of gas, price of corn syrup, and price of Snickers bars. And we do it like over enough samples over a long time. We observe this. And then we just SVD the matrix, and if we see something that's approximately rank 2, then we can conclude there is really some linear relationship. So again, I would get single value sigma 1, sigma 2, sigma 3, and if sigma 3 is pretty close to 0, then I can conclude it's almost rank 2. Or the thing is that in a real world, you will never have anything that's like perfectly ranked something. There will always be some amount of noise, and there will be some outliers here and there. But if this is fairly close to 0, then you can conclude that up to some noise, this is essentially linearly predicted. Or there can be some effects which you didn't account for, right? Maybe it also depends on weather or something else you haven't really accounted for. So yeah, this is cool because it really works in any dimension. So if I have like 20 measurements of something, and really if you were on a Wall Street making lots of money, then you will be doing probably like more complicated models than these toy examples, right? Yeah.
So if you ran that with the 3 inputs, and the sigma 2 was close to 0, would that say that one of your inputs didn't really matter?
You mean sigma 2 and sigma 3? You mean three measurements, and I have a bunch of data,
you're
right?
taking 3 measurements, but only one of the sigmas is meaningful. Does that mean
it's only rank 1?
Yeah.
So that means that the remaining 2 can be linearly predicted from the first one.
So only one of the things is important.
Yes, correct. Or in other words, the other 2 can be linearly predicted from the first one. Yes, you're right.
So you can just throw every input and let it decide which ones are the important ones.
Yes, that's the really cool thing about SVD in this like statistics types examples. So in general, this is about discovering linear patterns in data by forming the measurement matrix. So the measurement matrix, and this is going to what's going to be part of your project 6, the latent semantic analysis. So listen carefully or rewatch carefully. So the measurement matrix is like this. So here I have my number of dimensions of my measurements. So in the Snickers example it was 3, in the Bears example was 2, but in general could be D, like some number of dimensions. Probably not that huge, right? Maybe like 20 or something like. It depends really on the application. And here you have number of data. So I made the matrix like this because usually you will have lots of measurements, right? You can be measuring long time. Doesn't always have to be the case. And the measurements are the column vectors like this. And then the interesting thing is that if we are computing the left singular vectors, all we are looking at is AAT, where what is the dimension of AAT? So this was D times data, right? So the dimension of AAT is what? It's D times D. Interestingly, it doesn't depend on the number of your data samples at all, which is sort of interesting. If you take 1,000 measurements or 1,000,000 measurements, the dimension of this matrix will always be the same. Yeah, and then essentially the sigma, here you get the eigenvalues, which are the single value squared, and they indicate the importance of these directions. So the left singular vector corresponding to the highest singular value represents the direction where the data varied the most, the highest variance. That's why it's called sometimes the principal direction, the highest variance of your data, the most important component there. For example, when I was talking about this image compression example, where's my image? Somewhere. Here was my image. Like if my image was something that had like really strong bar here, like some strong feature here, then I would probably get some principal component which like reflects that thing there, right? That's like a principal direction corresponding to large single value is something that intuitively appears a lot in the data. That's the idea. Does that make sense? All linear algebra is doing is basically taking linear combinations, and if you have lots of data, it sort of discovers what linear combinations are most important, or what are the vectors such that their linear combinations can nicely approximate the rest of it. So it's important to realize that this is only linear. So actually I think I needed to correct something here. Idea of the intrinsic linear dimensionality of the data. So here we are really in linear algebra. So there are some nonlinear relationships in the data. Like for example, let's say we had just 2D measurements and they ended up modulo some noise, right? Doing something like this, right? So the optimal linear dimension of course is 2, right? But you could easily argue that there is actually an intrinsic nonlinear dimension, that the data lie all on a circle, and that only has one parameter, right? Just this angle. So the intrinsic, the like, how would intrinsic, I think is a good one. The real dimension of the data can be smaller than the optimal linear dimension. You can even have things like the Hilbert curve, which is like a space filling curve, right? The curve that can fill the space completely. But those are sort of esoteric things. It's not that this would not be important, but the point is that already discovering the linear relationships between the data can get you pretty far in many applications. So one of the applications that's important for you, because it's part of project 6, of part of our mini Google, is the latent semantic analysis. So that's another application in this vein. So here it's again like a web. We are analyzing websites, web pages, and they are just documents. And they are documents in some language, say English. So let's say we're only looking at English or web pages. And we consider that we look at every web page as a bag of words. So we have some dictionary. We have dictionary of all English words. And we just represent every site by the number of words it has. So how many instances of each word we have in the document. So we have like a dictionary, and there is like word 1, like then there's word 2, like B or something like that. There's word 3 and so on. And we just count how many times each word appeared in the document, like 3 times, 5 times, 0 times, 1 time, and so on. And this is our vector describing the document. So we essentially forget where the words were in the document. We just collect what words and how many times appeared in that document. And then imagine you have a web where you have a billion websites like this in English, right? And you represent every website using this bag of words representing vector. And then, of course, the cool thing is to run SVD on that, right? There's like lots of science essentially does collection of, well, lots of science is not correct, but there was lots of research that works like this. It takes a large collection of data and runs SVD on it, and then interprets the results in a cool way. So the latent semantic analysis wants to discover patterns in these documents. So if we run SVD on it, what the SVD is going to discover in the left single vectors are essentially some sort of representative documents, right? The point is, if I have my matrix, so every column of this matrix is a document represented as a bag of words. I have really many documents, right? Then I SVD it into some representation, just like this. Sorry about this overlap. So what this means is, again, taking linear combinations of the rows of this matrix. So one way I can interpret it is that in the rows, I have my bags of words that correspond to some topics. For example, this thing for a real web could discover that like in a legal document you have some set of words which are probably quite different than from like a sports article or like a technical computer graphics paper or so on. So like each of these topics would be one column of this matrix of left singular vectors. And this is what you can use to search for similar documents, because then you can use it to compute descriptors. If a new document comes, then you can project it on the space on the basis given by the columns of the U matrix, and then I can say these are my descriptors, and I can like classify, I can compare the similarity or dissimilarity of two documents, and that turns out to work pretty well.
What do you mean by projecting it on this?
Yeah, that's sorry, I just glossed over it. I mean, so if I get a document X, so what does it mean projecting onto the subspace? I mean doing UTX.
Okay.
So this is my matrix U. So if I want to project on the subspace, on the column space of U, then because the columns are orthonormal, then all I need to do is UTX. Is that true? Yes, it is. So basically, like if I ask the question in reverse, if I get a new document, represent it or approximate it as a linear combination of my topics. If I call the columns of U topics, that's the thing, that once I start giving the matrices some semantics, then I can start calling the singular vectors with like different names, because now they have some extra meaning, right? The matrix got some more meaning. Now I know I'm looking at documents, so these vectors also have some meaning. So that's sort of where the science sort of kicks in, if you want. Here is another and probably final example we can manage today is eigenfaces. That's also pretty cool. So it's sort of similar to the matrix, to the image compression example I started with, except that now we have like a collection of images, like tons of images of faces. And they are sort of like normalized, that the face is always like in the middle and like nicely centered and so on, and you can probably assume that with some normal lighting, nothing so crazy. So then every image you can take and unroll as a column vector in a matrix, right? Again, you obtain like a huge matrix and you SVD it. And what happens, what you get out of the SVDing it, what you get as the left singular vectors are so-called eigenfaces. That's how these eigen things happen to be. Basically, you just take some data which represents something. They represent faces in this case. And then SVD discovers the most important representatives of that set. And in this case, those are the eigenfaces. Here is an example of that. Then you can use it for lots of applications. You can use it to compress a face, of course. You can use it to compare two faces, to extract features, again, by projecting it on the space of your eigenfaces. There's other applications. There's one on analyzing and compressing motion capture data. You can really compress anything, so motion capture data being no exception. And I will just quickly mention before I need to finish. You can also do subspace dynamics, where the basic idea again being taking some principal modes of deformation, which can also be understood as singular vectors of deformations of some elastic body. I might cover this in phys-based.
Is that the Eiffel Tower?
Yes, it's that. Jarno actually was here a couple weeks ago. He visited, and that's what he does. Yes. All right, so we should wrap up. Any more questions? I would love to explain. Maybe I can explain that later if we still have time during the week. So the project 6 is not due this Friday because it's Thanksgiving. It's due the next Friday. I think December 6th or something like that. All right. Okay.